And we'll go from current slide here. But before we get going on that, let me there's a couple of announcements. This one is probably almost too late to make any difference. But on the Bessemer campus, maybe here on this campus too, but there's workforce development is one of the areas they have over there. And they have been asked to provide some line worker training for Alabama Power and other energy and utility companies and contractors that do work for them to train people to be line workers, going up the poles or using the bucket trucks to go up and work on the various lines there. It's a pretty extensive program. It goes from something like June the 8th to August 14th or something like that. 5 days a week, Monday through Friday, 8 to 4. I'm sure there's a lunch somewhere in there, so basically about 8 hours a day with a lunch somewhere in there, and 5 days a week for 9 weeks. Okay? Let me get your name, please. Rachel Sullivan, right? Okay. No, I mean Rachel Smith, right? No? Rachel Sullivan, I had it right. And?
Gamble.
Say it again?
Gamble.
Yeah, there you are, Gamble. Got it. Okay. I was saying there's a opportunity for some training and linemen, as in the people who climb power poles or that type of stuff. There's seems to be a need for it. They've asked for training. They're going to be offering it on the Bessemer campus. It includes a commercial driver's license, just all sorts of stuff. It's a pretty powerful seeming training. The bad news is the deadline for applying for it is today. I didn't have this email last week, so if you know of someone who that sounds like a dream job for, get on the phone for them right now and tell them to get in touch with the Bessemer campus Office of Workforce Development and to find out, because there's a website you go to apply. You need to do it today. So if you know of anyone that fits, let them know sooner rather than later, as in today. All right, the only other announcement I have is normally I have office hours on, let me see. Yeah, I'm recording. On the Birmingham West campus on Fridays from 8 to 12. Not this Friday. I've been assigned to go to Opelika, to Southern Union Community College. A group of us are going to work on course standards and things like this, and it's not an option. I've been assigned to go. I'll be leaving that campus over there sometime around 6 in the morning and coming back sometime around 5 in the evening. So in no way I'll be in my office from 8 to 12 on Friday. And because I'm going to be gone so much this Friday, when I'm supposed to do 4 hours, I'm going to see if I can get next Friday off as well, because I've got some personal things I would have to take care of. And so I may not be on campus next Friday as well. But we'll find out about that later. Okay, those are only 2 announcements. I know any questions. I know some people came in late. I'd ask, did everyone get a copy of Test 1? Oh, Test 1, the first test. You did not? You did? No, just the copy. Yeah, you've already turned it in. Right. Okay, anyone who did not get Test 1. How about Test 2? Okay. One? Just one person? Okay. That will be easy to reach. Well, I said it would be easy to reach. Here we go. Yeah. There's Test 2. So everybody, yes?
Are we going to get Test 1 back?
Yes. That's a good question. I was going to address it. Test 1, I have now received, well, how many I'm missing? There's 3 people at the top of the alphabet that I haven't seen for weeks, okay? Of course, we meet once a week. So I don't know if they're still involved or not, but they haven't turned it in. Then besides those, there's 2 other people haven't turned them in, and frankly, they haven't been seen for a while. But I know 2 people got it today, so when they get theirs turned in, I'll see if I can figure out whether the other people are going to be returning or not. What I don't want to happen is me return a test and then somebody lays eyes on correct answers and all of your grades are devalued because you earned your grade and someone saw the correct answers, because I usually write the correct answers on the test. So I want to make sure all are in that are going to come in, because I don't want that other possibility to happen. I don't want your grades devalued in any way. So as soon as I get them all in, I'll be returning them. They're all graded and the grades are out on Blackboard. They should be. And also, if you want to see what you missed, you can always do that right after class. If you come in before class, you can see them before class or after class. And you can always see that, but I can't return them to you permanently until I do get them all in. Okay. Good question. All right, any other questions or issues? Okay. We're almost finished with Chapter 8. That's why I passed out the second test last time. There's nothing that we've got yet to do that was on the test. Everything that's on the test we've already covered. It's just that the last section or 2 here talks about alternative energy sources. Now, what do we mean by that? I'll put a couple of these definitions down here just in case you don't have your books to look at. What we mean, let me get my pen set up, by alternative energy. Remember, energy cannot be created nor destroyed. So total energy is energy, okay? But what we mean by alternative energy is this is defined as a source of energy It's 8.5. We went through 8.4 last time. Yeah, okay. We finished 8.4 last time. Alternative energy is defined as a source of energy that does not originate from fossil fuels. I know my writing is sloppy, but sorry about that. If you've ever signed out of Home Depot or somewhere with an ionizing pen, you know what it's like to write with that, okay? And does not produce significant undesirable byproducts. That's ugly writing. Byproducts. That's a P there. Undesirable byproducts. That could harm the environment. Okay. All right. Can anyone think of some alternative energies that we've been using for years? Last weekend, my wife and I went up to Smith Lake. Does anyone know what Smith Lake is? There is on the, which river is that? Maybe the Warrior River? Many years ago, they built a dam. What kind of dam is that? A hydroelectric dam. Okay, now think of that. That produces energy, doesn't rely on fossil fuels at all. Now, building the dam in some senses did, okay, but that's been a long time ago. And it doesn't produce any what I would consider undesirable byproducts, okay? Certainly those that could harm the environment. Now, some people may argue, but it floods a lot of area, that maybe that does, in some sense, harm the environment, but not really. I mean, those were generally, back at the time they built it, were areas that were underpopulated, and probably people got a pretty good deal when they sold their land to the power company or to whoever it was that was doing it. So by and large, hydroelectric energy is that way. You think they'll be building very many new hydroelectric plants? Probably not, and here are the reasons. Most of the easily dammed rivers have been dammed, probably for years. You have to be in an area like where Smith Lake is, where it goes deep really fast. You don't want to dam bump a river that's very flat around there, because if you did that, you're eating tons of acres of land. Smith Lake is what they call a finger lake. There's just all these fingers that used to be really sharp ravines and valleys in there. That's what filled up with water. And that, you get a large drop, the drop in the water, that's what gives you the energy. Where you have a flat area, to build a large drop, you cover just tons and tons of acres, and you destroy a lot of habitat for lots of things. So most of the easily dammed rivers have been dammed, okay? Probably not going to be too many more built. Besides, our population has increased, and there's people living along most of those rivers, probably not wanting to have to give up their riverfront property. Can anyone think of some energy sources? Okay, I know you can think of those fossil fuels. Anything that depends on coal, natural gas, petroleum. Those are all fossil fuels. So exclude those. All the power plants that burn coal, burn natural gas, or possibly petroleum products, some of those are all not alternative energy. What is another one that doesn't use fossil fuels? Yes? Wind power, excellent. That is definitely an alternative energy source. We don't have many of those in Alabama, okay? Out on the West Coast, lots of them. Midwest, quite a few. Far West, quite a few. Can we do more? Probably, especially here in the Southeast. Any others? Definitely a good alternative energy source. No negative byproducts, no fossil fuels. Any others? How about nuclear power? No fossil fuels there, is there? Is that an alternative energy source? Yay or nay? What you think? Excuse me? Sorry. Would that be an alternative energy source by this definition? Get your name, please? Bell. Okay. Katisha?
Yes, sir.
Okay. All right. Question, did you get test 1 or test 2?
Yeah, I didn't finish it. I have a couple questions.
I'm sorry?
I didn't finish it because I have a couple questions on it.
Test 1. Did you get test 2?
No, I didn't.
Okay, let me go on and get you test 2 before I forget to give it to you. I passed these out last week. We haven't quite finished the chapter, but we finished everything that had any questions on it. only get one. Okay. All right. The question's out there. Would, by this definition, nuclear energy count as an alternative energy source? No fossil fuels involved. What's the second criterion? What follows the and here? Okay, what you think about that? Nuclear energy, does it produce any undesirable byproducts? Nothing except the nuclear waste. And the nuclear waste is not very desirable. Okay, there's not huge amounts of it, but there is some. And the other thing is that could harm the environment. Have you ever heard of Chernobyl? No. It was a nuclear power plant built by the Soviet Union in what's current day Ukraine, and they had a really major meltdown there that killed, I'm not even sure people know how many people died from that. And I'm very sure they don't know how many people were harmed by that. And the reason I'm sure they don't know, because it's still harming people, and they may not know it, okay? It was a major, major, major nuclear disaster, because the nuclear byproducts, after it melted down, it's still emitting enormous amounts of radiation. No one can live anywhere close to it today and for the foreseeable future, okay? Could definitely harm the environment, okay, and people around it. 3 Mile Island, has anyone heard of that? I can't remember exactly where it was, Pennsylvania, New York, somewhere up there, a nuclear power plant here in the U.S. that came this close to having a major nuclear meltdown. It did have a meltdown, but it was pretty much contained. I'm sure some lives were lost, and probably some people got radiation sickness and things from it, but it was not nearly the major disaster Chernobyl was. Any of you ever heard of Fukushima? Fukushima was a nuclear power plant off the coast of, or on the coast of Japan, and unfortunately Japan is on a fault zone, a fault line, shifting plates, okay? And there was a major earthquake just off the coast of Japan that created a tidal wave that flooded Fukushima nuclear power plant. And when it did, they lost power. When they lost power, they had no control of the nuclear power generation yet. The plant melted down. I mean, major. It was probably as bad as Chernobyl, except they had all sorts of backups, safety features built into the plant to contain it. So they did have, I'm pretty sure, some loss of life, nothing like Chernobyl. Now, the jury's still out whether there's still going to be major harm. It polluted parts of the Pacific Ocean, near Japan. How serious that is, we don't know. We probably won't know for a generation or two. Whether people get sick from eating the seafood, if the seafood even lives. It could create dead zones. I mean, it definitely could harm the environment. And that was not by any, the first two, Chernobyl and 3 Mile Island, I'm pretty sure man had something to do. Somebody failed to do something, someone messed something up, hit the wrong switch. Something happened that made that shut down, melt down. The one in Fukushima, totally done by nature. No one could have stopped it or minimized it any more than was, except, of course, not building a plant near a fault zone. But guess what? All of Japan is on the fault line, so it's sort of hard for them not to build one there. So I don't think you could probably count nuclear power, even though it's no fossil fuels, wouldn't be considered alternative fuel source by this definition because there are undesirable byproducts. Either the risk of meltdown, but then just the nuclear waste. Right now, I don't even know what they're doing with nuclear waste now. For a long time, they were burying it in a mountain somewhere out in Utah. I think it was either called White Mountain or Green Mountain or some sort of name like that. And they were burying it in caves deep in the mountains. And they were sealing it up as well as they could. But that nuclear waste lives on. It is dangerous for nuclear radiation for thousands of years. And sealing it as well as they can and doing everything, burying it under mountains and stuff like this, we still don't know if those containers are going to hold for thousands of years, if something might happen, that something breaks, cracks, explodes. We don't know what's going to happen. It could damage groundwater. It could do all sorts of things. I'm not sure Utah is letting them put any more down there, so I don't know what they're doing with it now. There was actually one time, shortly after my wife and I moved here to Birmingham, I'd say within the first year or two that we lived here, there was a proposal to ship nuclear waste by rail, through Birmingham, probably through Tuscaloosa, and take it down to Greene County and put it in a landfill. And it got that close to getting done. I think they stopped the train just before it reached Alabama and said, no, we're not going to take it. But it had almost snuck its way through, and they were going to bury it in a poor area of Alabama, which was upstream from a river that runs down to the Gulf. And if there had been nuclear waste leakage anywhere there, groundwater everywhere south of there could have been contaminated. People could have been contaminated. Animals, plant life, everything could have been contaminated. Fortunately, they got that stopped in time. So I would say there are byproducts there. Okay, but hydroelectric was mentioned. Wind was mentioned. One other I know I can think of right now. Any of you have a calculator handy? Anyone? Especially an older calculator, maybe a scientific calculator that you never have to charge.
Solar calculators.
Second?
Solar calculators?
Yes, solar energy. That is a non-fossil fuel, produces no undesirable byproducts. So solar, wind, hydroelectric, these are some of the alternative fuel sources, okay? Alternative energy sources. Another is geothermal. Okay, what do we mean by that? So let me, because these are highlighted in your book, let me go and that's hydroelectric. Okay, wind. Geothermal. What in the world could geothermal mean? Geo comes from what? Geography, geology, geo. Say again? The earth, that's where it comes from. Okay, thermal means heat, okay? Where is heat coming from the earth? Does the word Vesuvius come to mind? Never heard of Mount Vesuvius? How about Mount St. Helens. Never heard of that. Say again?
Volcano.
Volcanoes, of course. Okay, now, it doesn't have to be a volcano, but volcanoes produce from the earth lots of heat. That's because inside the earth, there's a lot of heat, because you have the atmosphere, which is a lot, but then layer on layer on layer on layer on layer, pushing down pressure, and things are always moving. Atoms and molecules are always moving. Rub your hands together, pressing them together. What do you notice? They heat up. And that's what's happening inside the earth, and to the extent that it melts the rock, molten rock. And that's what volcanoes emit. It's called magma when it's molten rock. When it reaches the surface, it's called lava. So if you can tap in to some of that heat that's down there, you can produce geothermal energy. It's non-fossil fuel and no negative byproducts. Okay? One place that's done that big time is Iceland. Iceland? That's on, what's the first three letters of Iceland? Ice, okay? That's cold. Incredibly cold up there. But the nation of Iceland is a series of islands that are volcanic islands. And some of them are fairly active. I mean, not super active. But in my lifetime, they've had some fairly major explosions. One, the most recently I remember, actually shut down airports in Europe, England and Europe, because there was enough volcanic ash in the air. They didn't want the planes taking off, sucking in that into their expensive jet engines. So they actually shut down airports because of eruptions on Iceland. Well, what they've done in Iceland, no matter how cold it is, they pumped water down next to some of that hot rock that's in conjunction with the volcanic activity, and pump that up, pump it under the city streets, into people's homes, and that's how they heat their homes. They don't pay for a bit of heat, or they may pay a little bit for pumping of the water in, but hardly anything. They don't have to, even though it's a cold, cold, miserable place, the energy there is very cheap, at least heating energy. Now, we have some places in the U.S. that have that. Hawaii is a volcanic island chain. They use geothermal and produce a lot of their electricity. They don't have fuel. They don't have gas, natural gas. They don't have coal. They're volcanic islands, okay? They don't have those kinds of resources, and because of that, they use geothermal. Places in the Pacific Northwest where you have volcanoes like Mount St. Helens, like Mount Shasta, like Mount Rainier, those are all pretty much extinct volcanoes, but they still have access to hot rock. And where you have hot rock, you can get geothermal energy. And then we mentioned solar. Solar certainly is not dependent on fossil fuels and no negative byproducts. Those are the ones we know about now. There are probably some that will come up, hopefully some that will come up in the future that we can depend on as well. There is a little physics connection on wind energy worth your look, and probably the one on physics on the job, wind turbine technician. There's a glossary that follows beginning on pages 227 and then goes on to a formula of 8 formulas in 228. Review questions are good to look at and think through, but the review problems, those are the better ones, because that's going to be more like what your test questions are, and any of those odds probably have answers in the back of the book. There's an applied concept there that's probably worth your while. In fact, let's get out of this, and one of those applied concepts is this. All right, here's another roller coaster problem. What is this illustrating? What principle did we hit this chapter that we talked about here? conservation of mechanical energy. Mechanical energy is the sum of kinetic, which is the energy of motion, and potential, which is the energy of position. Up here, 0 miles per hour, what would be the kinetic energy up there? 0, because the kinetic energy is the energy of motion. If the velocity is 0, there is no motion. Kinetic energy is 1/2 mv squared. If v is 0, it's not. But the fact that this is 60 meters up, which is pretty high, by the way, what kind of energy does it have? Position, which is potential energy, gravitational potential energy. So you could calculate the gravitational potential energy here if you knew its mass, and you knew that's all you need. mgh, that's the gravitational potential energy. We know what g is. Since this is in meters, which g would we use? 2 acceleration, 2 to gravity. One in the SI unit, one in the US customary. Which one would we use for meters? SI, and what is G in the SI units? 9.8 meters per second squared. So with that, we could calculate the gravitational potential energy if we knew the mass of that car. When it gets down here, this was our 0 reference level, because that's as low as this car will ever go in what we see here. Okay? So, that's the 0 reference level. So that's where its potential energy would go to 0. So what would be maximum? Here, 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 and here. Kinetic energy. All the potential energy it has here, that would all be kinetic energy down here, because the sum of those is mechanical energy, and mechanical energy is conserved. Supposedly. You know, on a roller coaster like that, you're going to have a little bit of friction, so it's going to decrease a little bit because you're going to lose some due to friction. But, in an ideal situation, so if this is 20 meters here, tall here at point B, that means you have 1/3 of your gravitational potential energy you did here. That means 2/3 of your total energy will be kinetic, like this. Here it's 30, so half of it will be kinetic, and half of it will be potential. Over here it's 40, so half of that will be gravitational potential energy. I mean, 2/3 will be gravitational potential energy. 1/3 of the original would be kinetic energy. So it's going fastest down here, next fastest at B, then at C, then at D. Okay? Does that make sense? You can work the problem they have there with that. I thought since they had it in the slide, it would be a good review. And that's it for Chapter 8. And from Chapter 8, we move to see if I can get this out of the way. Chapter 12. All right. Skipping 9, 10, and 11. Sorry you had to buy a book that we're skipping so many chapters for, but Chapter 12 is the chapter dealing with matter. And I can't remember exactly how it was expressed in your course description, but this was one of the issues that it was talking about, that you had to be exposed to the physics of matter. So let's get this going from current slide. All right. Maybe some definitions are in order. What in the world, let me get my pen back. What in the world is matter? Anything that occupies space and has mass. Okay? Now we talked about mass back in Chapter 5. That's how much of a substance there is. Okay? And of course it also has to occupy space. Now, they're leading up to something else here. Don't know if we can get all this on this slide. I imagine we're going to have to go to another slide. So let me get out of this and go to a clean page here. What they're describing here at the first page, this is page 310 under 12.1. It's an old concept. It's first developed by an ancient Greek. I'm guessing probably 400 to 500 to 600 years BC, way back then. And he was a thinker. He said, what if I have a piece of iron here? Okay? What if I break that into two pieces of iron? And take the smaller piece and break it into two pieces. And take his smaller piece and break it, and just keep doing that, and keep doing that, and keep doing that, breaking and breaking and breaking. Is there any point where I come to the smallest piece of iron that I can have and it still be iron? In other words, you can't divide it any further. He said, yes, it seems like there has to be that. Now, of course, he couldn't do it. He didn't have the technology to do it. But he called that indivisible piece of iron an atom of iron. Atom in Greek means, it comes from the Greek word meaning indivisible. Okay. So we got two things going on here. I'm going to call them two scales. Okay? We've got the, y'all want to go big first or small first? I don't care. Pick one. Big or small? Big? Okay. So let's take, I'm going to call that the macro scale, the big scale. And then we have the micro scale, the small scale. Okay? When I say micro, we're talking about those individual atoms. So let's take, on the micro scale, atom. That's the smallest particle of matter that you can have and still be that matter. Okay? And I'm going to pair that with the word elements. Do any of you have enough chemistry to know what I mean by the elements? Yes, very good. I've looked in this book and I can't find the periodic table. If y'all can find one, show me where it is. They do have a listing, I think in the back somewhere here, of a listing of the elements, but it's not in the periodic table, which I find is the most useful way to list them. But now I can't even lay my hands on that, so that's maybe after this one. Oh wait, there's a periodic table. Back on page 694, there's a periodic table. The things listed here are the elements. Now, what makes an element an element? Now, element is a macroscopic term, big scale, okay? Some of them listed here: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, on and on and on. Now, they don't give the names, but those are just the symbols for them. These are the things that are made up all of the same kind of atoms. Every atom is the same, okay? That makes an element. The smallest particle that will be an element, that element can have, is an atom, okay? So, that's the next definition they give here. A substance that cannot be separated into simpler substances. It's a good way to say it. Okay, that's what an element is. Now, what do we get if you combine two or more elements together? Anyone know that chemical term? Almost sounds like combine, but not quite. A compound. Okay. A compound is a substance that contains, I can't write, two or more, and they probably should have different, but I'm just going to put it the way they do, elements. Okay, that's what a compound is. That's on the macroscopic scale. On the microscopic scale, these are made up of molecules. Okay? Compounds are made up of molecules. Now, elements are made up of molecules too. Usually they're single atom molecules. Or they're diatomic molecules, meaning two atoms, but they're all the same. Like oxygen. You don't find oxygen as single O, oxygen. You find that it's O2, oxygen. That's what we breathe in, and we process it, and we breathe out something else. Nitrogen, N2. A lot of our gases are diatomic, but they're the same molecule, same atoms in that molecule. But a compound is a substance that contains two or more elements, two or more different kinds of atoms. Okay. Now let's just take some examples of that. We already said iron was an element, has all the same kind of atoms. What happens if you let iron sit outside, damp weather like this, for very long? What will it do?
Rust.
Oh, what is rust? Anyone know? Iron oxide. And iron oxide has very different characteristics from iron. It's not nearly as strong. You can probably scrape that off. You can peel it off, sand it off. So no, you've lost a lot of strength. So that's iron combined with oxygen. Not a good idea to have, but there's your compound. I mentioned you breathe in oxygen. Your body uses the oxygen for what? What do we use oxygen for? Yeah, we breathe it, but what do we use it for? What do our bodies use oxygen for? Or any of you got a temperature? Say again? It doesn't regulate it, it creates it. Do you have a temperature? Yes or no? What is it approximately? 98.6 unless you're sick, right? Okay. So let's hope you're all 98.6, right? The room is not 98.6. The room's more like 68. Why are you so much hotter than the room is? Because you're oxygenating, literally, you're burning fuel. You're burning sugars, starches, fats, carbohydrates. You're burning fuel. That's why you have a temperature. Now it's a controlled burn, okay? It's oxidation. Just like that rust is iron oxidizing. That's not really burning the metal, but it's oxidizing it. When you light a fire, you're burning cellulose or petroleum or something else, whatever you happen to be burning. Well, what comes out of that process of burning a carbohydrate? What do you breathe back out of your body? Carbon dioxide. Exactly. What comes out when you burn a fossil fuel, like gas or coal or anything else? Carbon dioxide. Okay? So carbon dioxide is coming out. Oxygen is an element. Carbon dioxide is a compound. It's made up of carbon and oxygen. Carbon dioxide. The di means two. CO2. One C, two oxygens. Okay? Another thing that comes out, if you had a cold piece of glass, like a mirror or something, and you breathe into it, what happens to the mirror? It what? Fogs up. What fogs it up?
Hot air?
Second?
Hot air?
Well, but what's in the hot air that fogs it up?
Carbon dioxide?
Okay, what if you had a glass? Now, I don't know if your sun-kissed thing, is that cold? Is it room temperature?
It's a little.
Little cold. Is there any, no, there's no moisture on it. But if you had a glass with ice water in it, that's moisture. That's condensation. Excellent. Water is another byproduct of combustion. Okay? Well, water is what we use to put out a fire, but also water is a byproduct of combustion. Water is not an element, it's a compound. You know what it is? I bet you do. H2O. Two hydrogens, one oxygen. So remember I said you were burning carbohydrates? Carbon, carbo, hydrogen, drate means oxygen. You're burning carbohydrates. Or hydrocarbons are just hydrogen and carbon. So you're burning hydrogen and carbon compounds, and you're releasing carbon dioxide, oxidized carbon, and water, which is oxidized hydrogen. So, boy, oxidation is all involved with it. So those are just examples of compounds contain two or more elements. I've already mentioned the molecule is the smallest particle I hate it they say this, of an element that can exist in free state and still retain, so I hate it they say element. I'm going to say compound. The smallest particle of a compound that still retains the characteristics of that compound. That's C in there. Now remember I said elements are also made up of molecules, but they're always the same atoms, okay? So you can call those molecules as well, but I want to specify sort of the difference here. Now, we've already given some examples of this. Carbon, which can exist in many forms, but basically most of the carbon is a black, soft, sort of like the soot in a fireplace. You know, that's what carbon is. Combine it with oxygen, which is a gas that supports combustion, and you get a clear gas that you can't see. So where did the color go for carbon? We don't know. Let me give you an even worse example than that. Better, maybe, I don't know. Anyone know what sodium is? Sodium. Say again? Yeah, sodium, yeah. Na, okay, sodium. It came from the Greek or Latin or somewhere where it's called natrium, that's why it's Na. But what is sodium? Anyone know? I bet you've never handled any sodium in your life. Ever. Okay? I almost guarantee it. Why? Because sodium is actually classified a metal, but it's a very soft metal, and it's a very soft metal that is also incredibly explosive. If you've ever seen pure sodium, say in a chemistry lab, I can almost guarantee you it was in the bottom of a jar, and it's sort of a yellowish kind of metal, if you could see, depending on the jar and stuff, covered with oil. Because if sodium ever is touched by or touches water, it explodes. Water, it explodes, okay? That's why I said you probably never touched any. Otherwise, you'd have a very serious burn. Incredibly serious burn, because you're made up mostly of water. And it would have exploded that and made a great amount of heat. So sodium is an explosive metal, soft metal. Anyone know what chlorine is? Any guesses? Chlorine. Chlorine is a green, poisonous gas. Some of the tanker cars that you don't see it frequently, but every now and then one of them will have on it chlorine. You know, on the trains that go by, you'll see chlorine. If one of those ever derails and that chlorine leaks out, everybody for miles around are evacuated. Because chlorine is a poisonous gas. Green, literally, okay? Now, what happens when you combine sodium with chlorine? A yellow explosive metal with a green poisonous gas. What do you get when you combine those two? Second? What is sodium chloride? Salt that you put on your food and you eat. You're eating an explosive yellow metal mixed with a green poisonous gas? No, it's a white crystal. Once they combine chemically to form molecules, they lose the characteristics that they did have and have totally new characteristics. Yeah, perfectly safe to eat that sodium chloride, as long as it's sodium chloride. Don't eat the sodium. So that's an example of how molecules, the smallest part of a compound that still retains the characteristics of that compound. That's salt. You break it down any further, you got an explosive metal or a poisonous gas. Don't break it down any further. Leave it in the molecular stage. Okay. And it would be very hard to do anyway. Okay. And then atom, to give its definition, the smallest particle. I'm sorry, I'm misspelling particle. Goodness, I can't believe that. I did it in two places here. Smallest particle of an element. See, I think they really meant to put compound on the other one, okay? That can exist in a stable or independent state. Okay, sort of a nebulous definition there. Okay, now, going back to that periodic table, if I can find it again. I hope I can. Man, don't tell me I've lost it. Maybe it was after that. I need to put me a marker in here. Ah, there it is. Let me find some piece of paper I can put there. I don't want to lose that. I'll put that one. Okay, if you look at that periodic table, it lists, and this could be a little old, up to 109 elements. Now, some of those don't even have names by them, okay? They don't have symbols by them. So there's probably fewer than that. But they think there are at least probably somewhere around 109, 110, 115, something like that elements. We may not have discovered them yet, but they think they probably are out there somehow, okay? 109. In effect, really 90 to 100 that are very common. A lot of these are not very common, okay? That's all. Compounds? Who knows? Almost uncountable, okay? The number of compounds that are out there. So you can combine elements in all sorts of ways to form various compounds. Okay, now let's get out of this and back to this one. Sorry, I have to keep going back and forth like this, but they have such terrible. Here's an example of, someone's already mentioned it. What's that? Hydrogen, hydrogen, H2O, which is water. I got wet there. No, okay. Water molecule composed of 2 hydrogen and 1 oxygen atoms. Now, did they just for some reason draw it strangely like that? Wouldn't it be hydrogen, oxygen, hydrogen? No, it's always at an angle like that. And here's why. Well, I won't want to get into too much why, but it's because most atoms, and there are ions, I'll put that in there too, like to have 8 electrons in their outermost shell. They just like having 8 in the outermost shell. Oxygen only has 6 normally, okay? Hydrogen only has 1. So what they do, they share those electrons here, giving oxygen 2 here and hydrogen 2 there. Because hydrogen is just too small to have 8, so it only has 2. It and helium only have 2 in their outer shell. They're the only ones that do. Okay? So now they're both happy, but there's 2 other pairs of hydrogen, of oxygen electrons to make up the 8. 2, 4, 6, 8. Okay? 2 of those are hydrogens. But they're sharing. They're friendly. They share. Okay? And because you have 4 pairs of 2, the only way you arrange 4 pairs of 2 electrons, because electrons tend to repel each other because they have the same charge, is to put them in a tetrahedral structure. 3 base here and 1 here, or turn it any way you want to, and that's what you got. So 2 of these are always going to be at an angle with each other. The other unpaired are going to be at another angle with each other. Okay? The reason I'm telling you this is this end of a hydrogen, of a water atom, a molecule, is always slightly positively charged because the oxygen sort of hogs the electron away from the hydrogen. A hydrogen only has 1 electron, okay? So its protons are sort of exposed here because its electrons are being shared over here. So this has a sort of a positive charge, and then these 2 unpaired electrons, 2 pairs of electrons, 4 electrons that are here, they're slightly negatively charged. So we have what we call a polar molecule. Water is a polar molecule. And because it is, it's one of the best solvents out there. Just think about it. Salt dissolves in water, sugar dissolves in water, lots of things dissolve in water, okay? In fact, just about any polar molecule will also dissolve in water. Now, things that won't dissolve in water would include non-polar molecules, like your oils and your waxes. They will not, they're not polar, so water can't separate them. It can't dissolve them, okay? So that's just something about a water molecule. Now, we'll just leave it like that. Come over here, and this is a sugar molecule. Happens to be glucose. which is one of the simplest sugars you got. That looks simple to you, okay? That is just about the simplest sugars. Glucose, sucrose, and fructose are all very simple sugars. They're very similar in how they're put together, they're just the orientations are a little different, okay? Now what this is made up of, 6 carbons, 12 hydrogens, and 6 oxygens. The carbons are these, 1, 2, 3, 4, 5, and 6. The oxygens are these, the greens, 1, 2, 3, 4, 5, and 6. And the hydrogens are 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? Those are your sugar molecules. And you can tell that's not balanced completely, so it's somewhat polar. Water will dissolve sugar like crazy. Okay? So, that's a sugar molecule. And that's a simple sugar. Okay? You get into your starches, huge things. You get into hydrocarbons, generally much bigger. Lots of things are a lot more complicated. That's a fairly simple sugar. Now, looking at this, you can see carbon forms typically 4 bonds. That means carbon, and if you look at carbon in the periodic table, you'll find that carbon is in the 4th column. Oxygen's in the 6th column. It has 6 electrons in its outer shell. Hydrogen's over here in the 1 column. It has 1 electron in its outer shell. Carbon's over there in the 4 column, which is 4 electrons. It wants to have 8, so it pairs 1 with a hydrogen here, 1 with a hydrogen there, 1 with the oxygen here, the other oxygen pairs with a hydrogen, this pairs with another carbon. And then all of these have 4 pairs around them. Except this one, and it has a double bond with that oxygen because there's no more place for it to bond, so it bonds. It shares 2 electrons. 1 electron pair here, 1 there. It's called the double bond. So all the carbons have 4 bonding units. All the oxygens have 2. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. All the hydrogens have 1. And that's because of the number of electrons in the outer shells. Wow. Okay. So that's how molecules are made. Very regular patterns. Okay? Now, remember good old Democritus? He said that an atom is indivisible. It's indivisible to still retain its characteristics. That atom of iron, that very smallest unit of iron, to be iron still, it's indivisible. However, and I've already been mentioning them now, every atom is made up of 3 parts. Okay? Let's see if we can find some place to do it. Well, here they're listed, but I don't have room for definitions. So let's go to the other slide and give the definitions for them. I've got to go get my pen back. Okay. Well, I didn't get it back, did I? Oh, there we go. I hope we got it. Yeah. Every atom is made up of 3 major components. There are some minor ones. We're not going to get into the minor at all. The first of these is the proton. Anyone know what a proton is?
It's a positive charge, right?
Yeah, very good. It has a positive charge. Okay? It also has a significant mass. We won't go into it, but it has significant mass. Okay? Anyone know a second particle that will make up an atom? A neutron. What about it?
It's uncharged.
Second?
It's uncharged.
Uncharged, no charge. Okay? And it has a significant mass. And in fact, just a little more massive, not much, a little more massive than a proton, but not very much. And the third one, the one I've been talking about already, electrons. Y'all are good. Okay, tell me about it. Negative charge, but insignificant mass. It has a mass, but boy, it is tiny. It is incredibly tiny, okay? We can't say no mass because it does have some. You can measure it, but boy, it is minimal, okay? Now, let's go back to the other table. I needed to write those. Let's go back to the other table we saw there. And this gives those masses and charges. Okay? These are awfully small masses, by the way. Okay? And see, the neutron is just slightly more massive than the proton. I mean, just very slightly more massive. Okay? But it's still pretty small. 10 to the minus 27 kilograms. That means you would have to write it as 0.0000000000000000000, something like 9 sets of those 3 zeros, or 8 2/3 before you have the 1675 or 1673. Now the electrons, though, are even smaller. You would have 10 sets of those 3 zeros, and then another, then you got your 9109, okay? So this is an order of 4, between 3 and 4. So a proton or a neutron is approximately 1,000 times more massive than an electron. They're all small, but an electron is tiny mass. Now, tiny measurement also, okay, let's think in terms of things that are a little small. Meters are pretty good sizes, right? But if you divide a meter into 1,000 equal pieces, a meter is about from one ear to the fingertip. That's about a meter, okay? If you divide that into 1,000 equal pieces, that meter would then be, this is called a millimeter, about the thickness of a dime. That's 1 millimeter, okay? So that would take this, since you divide it by 10 to the third, 1,000, that would make it 10 to the minus 13 millimeters, okay? That means you take this dime and slice it into 1,000 equal slices. That would get you 10 to the minus 11. Then another 1,000, then another 1,000. I mean, boy, that's so tiny, it's hard to even imagine. Okay? Incredibly small. But they can't even measure the diameter of an electron. It's got to have one, but they just can't measure it. The zero size of an electron is due to the lack of any internal structure. There's nothing there to measure. There is mass, so you can measure the mass, but just barely. But the diameter, you just can't measure it. Okay. And yet, even though it's so tiny mass and so tiny dimensions, it still has a minus 1 charge. Whereas this most massive thing, the neutron, has measurable mass, measurable diameter, even though it's mighty, mighty small, but absolutely no charge. And then the proton, which is just slightly less massive than this, basically the same size, it has a plus 1 charge. Okay. So those are the properties of the atomic particles. All they do is have mass and charge. And by the way, a proton is a proton, whether it's in iron or nickel or cobalt or oxygen or sodium or whatever, a proton is still a proton. But by the time you get a certain number of protons together with a certain number of neutrons, that's what makes up these various elements. Okay? And then you get those combined and you get the various compounds. So it's pretty amazing how they're put together. All right. So the protons and the neutrons, these live in what we call the nucleus of the atom. Okay? The center part of an atom okay, made up of protons and neutrons. Okay? Now picture this. These protons and neutrons, which have significant mass, have definite diameters, and there's a bunch of them. Okay? Well, for hydrogen, there's only one proton. For helium, there's 2 protons, 2 neutrons. For everything else, there's multiple protons and multiple neutrons. Okay? So quite a bit of mass there. And they are combined together in this nucleus, which is incredibly tiny. Incredibly tiny in size. Okay? So just about all the mass of an atom is in that nucleus. But flying around the nucleus are these electrons, which have incredibly small masses, about 1,000th to 10,000ths of the size of these masses, and almost no measurable diameter. And these electrons are flying all over out here. I mean, just way out here. Tiny little nucleus that has all the mass packed into it, and then these electrons with almost no mass are flying around it. Well, that's what makes the size of the atom, the electron cloud. Okay? That nucleus is almost negligible in size, but has all the mass. So with that in mind, and in between those electrons, it's just as blank as outer space. And when my older brother came home from college, I think his sophomore year, he said, most of everything is nothing. Okay? Meaning that most of the volume of everything, whatever you have, lead, gold, whatever, most of that volume is absolute outer space, because all the mass is packed into a tiny little nucleus, and the electrons are flying around here, basically in outer space, and they have very little mass and almost no size, yet they are defining the size of that atom. And they're made up of nothing. Most of everything is nothing. Okay. All right. There is another slide here, or picture here. I think I'm going to have to go back to my others to draw it. I've kind of described it, but I really probably would be helpful to draw it. Okay. Here is a hydrogen atom. Let me get my pen set up. Okay. It has that single little proton. I'm going to call it P with a plus, meaning it's a proton, one positive charge. Tiny little thing, but very massive. And then flying around it out here somewhere is that incredibly tiny little electron with a negative charge. That's what makes a hydrogen atom. Okay, that's all, folks. One proton, one electron. And where is the electron? Is it in one little orbit? No, it's somewhere around there, and that takes up the volume of the atom is made out of that, and all the mass pretty much is in that one little, the nucleus is a single proton. Okay? Now, I'm going to do the same thing with carbon. Okay? Now that carbon has 6 protons. So there's a proton, there's a proton, there's a proton, there's a proton, there's a 1, 2, 3, 4, 5, 6. What color do you want your neutrons to be? blue, okay? Light or dark? Carolina or just regular blue? Huh?
Dark.
Dark. Okay, we'll do that blue. Okay, it has 6 neutrons. And they are packed in here. I think I drew 6 of them. Okay? Now, I'll keep the electrons black, I guess, since I drew that first one black. It has of course, since it has 6 protons, it's got to have 6 electrons. Okay? Now, the 6 electrons, 2 of them are in the inner circle. So there's a little electron, and there's a little electron. They call that a shell. Okay? And outside of that are the 4 outer electrons. There's one, there's one, there's one, and well, not here. Ooh, that's not centered very well. But that's the, well, I should have used that other one, but I didn't. So I'll erase this one. Okay. Okay. That's ugly, isn't it? In your book, it looks a lot better than that. Okay. Those are the electrons. Now, they made them look like big old blue balls there. Hey, they're tiny. You can't even measure them. Okay. The protons and neutrons are small, but they are so much bigger than those electrons. Okay. And remember I said carbon could do 4 pairs? Well, guess what? One thing will pair with this one will pair with that one will pair with that one, and one will pair with that one. So that's where it hooks up with hydrogens, with oxygens, with something, or with another carbon, okay? Because it likes to have 8 around its outer shell, and that's where you get your 8. So that's why it always has 4 bonds. Some of them could be double bonds, some of them actually triple bonds, but it always has 4 bonds. Okay. Ernest Rutherford developed the concept of the atomic nucleus, and here's how he did it. I don't want to get too much into this, but it is pretty interesting. Before him, a guy, I think his name was J.J. Thomson or something like that, modeled his atom, he said, like plum pudding, okay? Plum pudding, I may have had it, I don't ever remember having it, but is a dough with raisins scattered in it. And that's what he figured the atom was. The dough would have been the neutrons and electrons, and protons, and then scattered around in the dough were these electrons. Okay, they knew they were very small, so that's what he figured. Well, Rutherford said, let's see what this looks like. If that's indeed a dough, that's, you know, these scattered things, not like I've drawn it here, that was not the idea at all. He said, let's fire some particles. They happen to be alpha particles, which is basically the nucleus of a helium. 2 protons, 2 electrons. Let's fire some alpha particles into gold. Gold is a massive, massive, massive atom. I mean, something like 50, 60, 70 some protons with more neutrons. I mean, it's really massive. So he figured if he fired these tiny little alpha particles into that, then they would be bouncing back all over the place, and that would let him have a pretty good idea of what the makeup was of that gold. Now gold, the reason he used gold, he wasn't all that rich or anything, but gold can be rolled into the finest of sheets. You know, aluminum foil is pretty fine, pretty small. Gold foil can be much thinner than that. In fact, has anyone ever heard of gold flake? I think it's what they call it, gold something. You can take it and just rub it on something and it makes it look gold. It is gold, but you know, it's just a very, very thin little sheet of gold. Put it on wood and it makes it look like gold. Put it on metal, it makes it look like gold. You know, it's called gold plate, maybe. You know, it's just so very, very thin. Okay? So he had some of this incredibly thin gold. So they figured as massive as the gold is, it's going to bounce these alpha particles just back like crazy. And he had his equipment set up to catch and see where they were bounced to see what the structure was. You know what he found out? And you know, this gold thing was several molecules thick, so there's not much way that most of them made it right on through. Didn't even deviate. And that's what led him to believe that most of everything is nothing. That most of this is outer space. You know, that dense, those alpha particles just went right through. Every now and then they would hit the nucleus and then bounce that like crazy. But the vast majority of them went right through because there was nothing to stop them. Absolutely nothing to stop them. Okay? So that's where he came up with this model, and as far as we know, that's the model we have. Okay. Now, finally we're getting to where this chapter is intending to take us, and these are the three, and this book calls them the states of matter. Most physics books today call them the phases of matter. Okay? Now let's see. Yeah. I think I'll go back to, well, that's not what I want to do. That's not what I want to do. This is what I want to do. Okay, go back to this and go to the next slide here. Okay. These are the three, and the book calls them states. I call them phases of matter. There's actually one more, and we'll get to that later. The first of these is a solid. Let me get my pen set up. I've got hiccups, sorry. What is a solid? What makes a solid a solid? A solid is a substance that has a definite shape and occupies a definite volume. Okay. All over the room here you see solids, right? This table solid, chair solid, metal solid, this cabinet solid, board solid. Okay, all these things are solids. They have a definite shape and a definite volume. Why do solids have definite shapes and definite volume? Because they vibrate. Okay, every atom, every molecule is always in motion. There's never one that is ever stopped. They're always in motion. But in a solid, it's only a vibrational motion, and these are vibrate in fixed positions. We call those the crystal structure. Crystal structure means there is a molecule in every place, and it's connected to certain other molecules, and that's what makes this crystal structure. They do vibrate, but they can't move relative to each other. That's why it has a fixed volume and a fixed shape. They do not move past each other. Okay? That's what makes a solid a solid. Now, I have a question for you. If you had a solid, how do you change its phase or its state to make it, say, a liquid? Say again? Yes, you add energy to it. What the energy does, it makes those vibrate faster and harder and more, because when you add heat, the motion increases. And generally, the volume increases just a little bit because they're bouncing against each other more strongly. And at some point, they break away from each other. They break out of their fixed positions, but they stay close to each other. So that's what makes a liquid a liquid. It has a definite shape. They still place close to each other, but now they move past each other, so they don't have a definite volume. So liquid molecules flow around and past each other. So a liquid is a substance that takes the shape of the container but has a definite volume. Okay, can I bum your liquid again a minute? Okay, see this liquid in here? I can turn it this way and it has that shape, that way, that shape. I can do all sorts of things. It takes the shape of the container, but it doesn't change its volume. Okay, yours does too, you just can't see it. Okay, right? But it has a definite volume, but it takes the shape of the container. And that's because the molecules can move past each other, but they stay in close proximity to each other. Okay? Now, how do you make this liquid become the third, a gas? Yes, add more heat to it. Add more energy to it. And what you do then, you break them away from each other so they're not staying close to each other, and now they're flying around individually, not ever interacting with each other. Except occasionally they'll bump into each other, but then elastically collide and bounce back off. Gas molecules move rapidly in all directions and collide occasionally. Most of the time they just fly past each other, but they don't stick. Liquids stick to each other. They stay in that definite shape. Gas, Okay, let me write down the definition, then I'll give you maybe some dumb examples. A gas is a substance that takes the shape of its container, just like a liquid, lousy writing, and they say the same volume of the container. In other words, it fills up whatever space it's in. Okay? Now, I'm guessing most of you know what ammonia is, right? What if I had a bottle of ammonia up here, and I put it in the corner and reached over there and took the lid off? And I said, I think I need to go to the office for a minute. Y'all just, take notes, study, do whatever. And I left. After a short while, you two would be rubbing your eyes, and it's not much longer you would. And in some length of time, the whole room would be smelling of ammonia, because the ammonia gas molecules would escape that bottle and fill up the whole room. And you ladies probably, and maybe you guys too, know when you put on some of the good smelling stuff, perfumes, cologne, something like that, that you don't have to be smelling your skin to do it. It escapes and surrounds you, And it would take a lot to fill up a whole room, but if you had a perfume and left it open long enough, you would be able to smell traces of it everywhere in the room. So it takes the shape of the container and the entire volume. It has no fixed volume. Okay. And that's because the molecules move rapidly in all directions, occasionally colliding, not as often as this is, but when they collide, they just bounce off each other. They don't stick. They don't stay in close proximity to each other. All right. The next thing we're going to do here is look at properties of the solid. Oh, yeah, okay. Boy, that's a long way down the road there. So let's go back to the other slide. Okay. And we're just going to talk about these and I'll try to do it really quickly. I don't do anything very quickly, but I'll try. These are properties of solids. Let me get my pen back. Yuck. Come on. Okay. Okay. The first of these is actually two of them. Cohesion and adhesion. Okay. Now what do we mean by cohesion? It's the force of attraction between like molecules. I can't spell. I can't write. This thing is driving me nuts. My screen moves on me too, and that makes it even harder. Okay. The force of attraction between like molecules. Okay? Co meaning like, hesion meaning sticking. Okay? Sticking together, easing with each other. That's cohesion. I've done this before in physics classes and physical science classes. Fill a container with water, or have a student fill a container with water, and tell me when they think it's full. They say, yeah, it's full. I say, well, see if you can add a little more. No, it's going to spill. See if you can add a little more. And almost always, they'll add a little more, and it's still filling. Add a little more, still filling. Add a little more, still filling. And after a while, you can see the water over the top of the container, and it hasn't started spilling yet. And that's because water molecules hang on to each other like crazy. Okay? That's what makes them a liquid. Okay? They're hanging on to each other like crazy. Remember I said one end of a water molecule is slightly positive. That's the hydrogen end. The oxygen end is slightly negative. That electrostatic attraction holds them together. We call that hydrostatic attraction. Okay? And that's what keeps water, and that's why you can overfill a container and it not spill. Okay? Now, force of attraction between like molecules. By the way, have any of you ever jumped into a pool, landed on your belly? Call it a belly flop. Does not feel good. Even though water is a liquid. And they hang on to each other like crazy. It hurts. It feels almost like, it's not like concrete, but it feels almost like that. That's why it hurts so much. Okay? Now, the second of these is adhesion. Force of attraction between unlike molecules. Different or unlike molecules. That's ugly writing, okay? Okay. For instance there, maybe go home and try this, you know. If you have a clear container that you can see through, I would say preferably glass. You know, plastic will work okay too. But put the water in there, and you'll notice the water sort of crawls up the side of the container. Now, if you had a smaller and smaller container like a straw, put it in, and you'll see water actually rise in the straw. And we're going to see pictures of this later. Okay, so don't sweat this, but try it. And the reason is water is attracted to the glass. That's adhesion. It adheres to the glass and pulls up other water molecules with it. Okay? Does anyone know what ultimately that's called? Capillary action. And a capillary, have you ever had blood taken, just a small bit of blood? They just prick your finger and then take this tiny little tube and just hold it next to the blood, and it sucks the blood right up in it. You've seen that. You may have even done that, right? What sucks it up is adhesion. The blood adheres to the size of that tiny little capillary tube and just goes right up in it. And then they take that and do the blood work with it. That's adhesion. What word do we get out of this? Think of tapes. Adhesive tape. It sticks, unlike things together. Okay? Adhesion. Okay. Another property or principle is tensile strength. This is of solids. Oh, and I've been talking as if they're, liquids also have cohesion and adhesion. I've used those examples. So do solids, okay? We're talking about properties of solid, and here I'm using liquid examples, okay? Tensile strength is a measure of its resistance to being pulled apart. Okay. Tension is a pulling on something. That's tension. So this is the measure of its resistance to being pulled apart. Now, catch this ratio because you're going to see it over and over again. It's a force divided by an area. Force per unit area. This could be a rod, it could be a wire, it could be something like that. And here's maybe a dumb example, but it could be. Just say, take a rubber band, cut it until it's just a long length, and tie something to the end, and it's going to stretch, right? Because that's not got a lot of tensile strength. And then try put something heavier, and it'll stretch a little further, and heavier, it'll stretch a little further. At some point, it'll break. But it did tend to stay together, tensile strength. So the force per unit area. Now, that rubber band didn't have a lot of area, but it did. But think of doing that with a wire. Putting a mass or a weight on a wire, and it's going to hold force per unit area, but then do more and more and more. At some point, you're going to break the wire, okay? The amount of force per unit area, that is a tensile. That is what we use to measure tensile strength. The measure of the resistance to being pulled apart. Wires will have greater tensile strength than rubber bands, okay? And different metals will have greater tensile strength than other metals. The next one is hardness. Okay. The hardness of a solid is a measure of the internal resistance to the molecules being pulled, forced farther apart or closer together. Okay? A measure of the internal strength. My writing is terrible. Internal resistance of its molecules to being forced farther apart or closer together. Okay. That's hardness. Okay. I'm going to pull on the back of this chair. Hey, I moved it some. Pull on the side of the table. I'm not making much progress there. Okay? That's because the table is harder than the chair. Okay? That plastic on the chair is somewhat plastic. Or pulling them apart. over on the Bessemer campus today, I saw someone put out in the hallway 2 desks made out of similar plastic. Someone sat down on them too hard and it pulled it apart. Try doing that with this one. I don't think so, because that is a much harder seeming material. More resistance to being pulled apart or pressed closer together. Hardness. Now, there's several scales that measure hardness. They mention here the Brunel method, named after Johann Brunel. And you don't need to know that, but since it's in the book and highlighted, the Brunel method, Brinell method. That's one way of measuring hardness. In geology, they use the Mohs scale. You know, soft materials like talc are number 1. Number 2 would be something else. That's called the Mohs scale. The hardest thing on that scale is diamond, number 10. Nothing is harder than diamond. Nothing naturally occurring material anyway. Okay? And what the technique uses is the mass placed on an object okay, a chair, a desk, or whatever it is, divided by the surface area. Okay, of the impression. If it did make an impression, okay, I'm not going to spell it out. Okay, and again, the other was force per unit area. This is mass per unit area. Very closely related, but it's measuring different things. That's tensile, pulling apart. This is hardness, resisting being pressed closer together or pulled further apart. By the way, Johann August Brunel was born in Sweden, okay, if you needed to know that. Okay, another, now this is sort of related to tensile strength. This is called ductility. It has nothing to do with ducts. This is D-U-C-T, tility. Now these are just words. You don't need to know that much about this. Is a property of a metal, again a solid, okay, that enables it to be drawn through a die by the way, a die is a very small hole, okay, to produce a wire. Okay, one of the most ductile of our metals is copper. That's why we have copper wiring, because I bet you the wire in here is copper. You can stretch, force it through a hole and come out a long wire. Kind of the opposite of tensile strength, because it will stretch and stretch and stretch. And copper also will bend easily. Later, I don't know if we'll get to it in this course, but you'll probably run into it sometime. The very best electrical conductor is not copper, silver. Copper is just behind. It's very close to a good conductor. So why don't we make our wires out of silver rather than copper? Any ideas? Silver is way too expensive, okay? That's one. I thought y'all would come up with that right away. If you had things made out of silver wire, people are always stealing your wire, okay? It's really valuable. But that's only one reason. The second reason, silver is not very ductile. You can't make silver into very thin wires, okay? So ductility. Going to have to go to a clean page, okay? I'm taking way too long on this, okay? Is malleability. This is number 5, malleability. That's one that I have to look at how to spell. This is something, that's an L there, not a T. Okay. This is something I was talking about before with gold. It's the property of a metal. Why is my pen so short here? Okay. Most of these are metals we're talking about now. That enables it to be hammered or rolled now, not one type of hammer, that's not one type, into a sheet. Okay, that's what I was talking about, aluminum. Aluminum will roll into very thin sheets. We call that aluminum foil, okay? Gold will roll into even thinner sheets. So this is kind of the opposite of hardness. Hardness is resisting to be pressed together or pulled apart. Malleability is the ease at which it's rolled into a sheet. Steel can be rolled into a sheet, not very easily. What do they do to roll steel into a sheet? Heat it up, okay? Big time heat it up, okay? And that's basically how they get sheet metal and things like this. Make it very hot and then it's more malleable, okay? So that's malleability. This one we hit before in the last chapter, elasticity. What does that mean again? We talked about it before. What was that one? Measure of a deformed object. What would it do? Comes back to its original shape. Measure of a deformed object's ability. I keep crossing that L. To return to its original shape. That's what we mean by elasticity. Not how much it stresses, but how much it returns. Original size and shape after the forces are removed. Okay? And under this, we talk about the elastic limit. Most materials, say especially metals, you can deform them some and they'll come back. Deform a little more, they come back. Deform a little more. At some point, though, you deform it and it doesn't come back. That's its elastic limit. You pass the elastic limit. The maximum you can deform it where it will come back. And I used the example before of the little springs that used to be in ballpoint pens. You know what I'm talking about? You ever play with those some? You stretch them, they come back. Press them together, they come back. Stretch them, they come back. Stretch them, and oops, won't come back. You pass the elastic limit. That's what that means. The maximum, the point beyond which it will not return to the original shape. I'm just going to put return. You understand what it's talking about there. Okay. Now, under that, how we measure it, and let's see, let me go and get out of here. This is where this slide comes from. Here's that spring, right? The spring before stretching, you stretch it. As long as when you release, it comes back to that original shape. When I see this spring, I think of my garage door. It's got a big spring up there that pulls it up and do that. We've had before, it happened, one of those is broken. it reached its fracture limit and actually broke. I was glad I wasn't underneath that thing when it popped, okay? But at some point when it's near its elastic limit, it always comes back. But when it's beyond that, now it becomes plastic. Doesn't return to its original shape. And you keep stressing, like that spring did in the garage door, and it actually breaks. That's called the fracture limit, okay? So those were the pictures that show that. Now, how we measure that, the amount of force we put on it is called the stress. Okay? Well, my pen won't come on. There it goes. The stress is the ratio of the outside applied force to the area over which it acts. This is a lot of words here. Outside applied force ratio of that to the area, and the area, no, to the area I think is better. Over which it acts. And again, look at that ratio again. Force per unit area. We saw that earlier. We see it again. You'll keep seeing it. This is one of the big ratios that we study in physics, and it measures lots of different things. I think before it was ductility. No. Tensile strength. Tensile strength, stress. We'll see it in many, many areas here. Okay? Now, we're basically out of time. So what we'll do, if I can find my eraser here, there it is, we'll pick up next time with stress. I just gave you the formula. Stress is equal to force per unit area. So we'll pick up with the units for stress. So that will be right about the middle of the page. We'll pick up the units for stress. All right, good deal. Not any new homework exercises here, so work on your test. We'll finally get to some homework exercises in the last part of this section when we get to Hooke's Law. And there we'll hit some examples. Okay? We're almost there. Almost there. I know y'all hate not having problems to work on.
This is the 10.
This is number 10.
On number 10, what formula do you have to use to find the height?
Okay. A lot of it is thinking. Okay? 55-gram bullet with 3 single digits is fired vertically with an initial velocity of 123 meters per second. So you got a bullet going up, that. Okay? Now, what is its velocity at the highest point of travel?
Nothing, because it's supposed
Absolutely, because it stops going up and starts to fall down. So that, yeah, you got that one. Good. Okay? What maximum height does it reach? Okay? Remember the formula. Yuck, I'm all tied up. Sorry. I get loose. Remember the formula that's something like this. S, I believe, is what we used in here, is equal to negative 1/2 GT squared plus V0T plus S0. That's initial displacement. You don't have an initial displacement here, but you do have an initial velocity, and you do have, is that what it's asking? No, okay, I'm sorry, that's a different formula. Maximum height does it reach? Sorry, that's not the one. I'm going to go and erase all these. Okay. All right. S. Yeah, that, okay. I know a formula, I can't remember if we used it. Let me find the one that we used. This is the second one, right? Oh, bring it back. Use your energy. Okay, you're going to have to get this to kilograms. You need to get that to kilograms, so you got to do a unit conversion there. And you have, this is a velocity here, right? So this together, and you fired it from ground level, right? Mm-hmm. So this is going to be your kinetic energy formula at the bottom, right? Right?
I'm not following.
Huh?
I'm not, I don't think I get it.
Yeah, kinetic energy. We did that back in that chapter, okay? But then, at the top, when it reaches that zero velocity, where it has no kinetic energy, all its energy up there is gravitational potential energy. Oh, okay. They call this E sub k 1/2 mv squared. We know that. We don't. Yeah, we know the mass, but get it into kilograms. And then they call this E sub p for potential energy, though it should be gravitational potential energy. And this is mgh. And remember what we did? We set these equal to each other. This at the bottom is equal to this at the top. And then you solve for, I think we solved for h. I mean, for v before, this time solve for h. That'll be the maximum
So
height.
it's mgh equals a half.
Yeah.
Yeah, just do
M,
that and then solve for h.
mgh is equal to 1/2 mv squared. This time solve for h, and the first thing that's going to happen, the m's are going to go out, and the h is equal to v squared over 2g. I think you'll find that comes up to be your height. And then the last one will surprise you, I think, but think through it. I think you'll get that one.
The last one.
What is the question there?
The last one is what velocity was it in the ground?
When it's coming down. Well, guess what?
Go up and then go down the same speed.
Yeah, exactly. Good deal. Yes, ma'am.
I was going to ask a couple things. What did I make on test 1?
Okay.
I'm a little nervous because I was used I've taken like a physics test before, and I used 9.81. So on that test, I did 9.81.
Yeah.
But on this test, I'm doing 9.0. I didn't realize I did that until I turned the test in. So I don't know if you counted off.
Remind me, are you Summer?
Mm-hmm.
Okay. Okay. You scored a 91.
Okay.
That's good.
I didn't literally when I
Oh, wait.
plugged it in.
I don't need to be recording this.